Acids, bases, and pH, the chemical world within water. The water we drink every day may appear simple and transparent, but inside it, continuous chemical reactions are taking place. Depending on whether a substance is acidic or basic, the reactions vary, and these properties can be expressed by a value called pH. Today, we'll explore the acids, bases, and pH of the water we encounter in our daily lives. Water is more than just H2O, it has a complex chemical world, and within each tiny droplet, fascinating chemical reactions occur. Let's dive into the incredible story of chemistry inside water. 1. What are acids and bases? In chemistry, acids and bases are fundamental concepts. When they react with water, they exhibit unique properties, triggering various chemical changes. An acid is typically defined as a substance that releases hydrogen ions, H+, in an aqueous solution. Examples include acetic acid, CH₃COOH, found in vinegar, or carbonic acid, H2CO3, which forms when carbon dioxide dissolves in water. Acidic substances often have a sour taste and can react with metals to produce hydrogen gas. A base is a substance that releases hydroxide ions, O-, in an aqueous solution. Common examples include sodium hydroxide, NaO, and calcium hydroxide, CaO2. Bases usually have a bitter taste and feel slippery to the touch. Moreover, bases react with acids to form water and salts through a process known as neutralization. 2. What is pH? pH is a scale that measures the acidity or basicity of a substance, representing the concentration of hydrogen ions. It ranges from 0 to 14, with 7 being neutral. A pH below 7 indicates acidity, and a pH above 7 indicates basicity. pH 0 to 6, acidic, higher concentration of H+ ions, pH 7, neutral, for example, pure water, pH 8 to 14, basic, higher concentration of O- ions. pH is a logarithmic scale, meaning that each whole number change in pH corresponds to a tenfold difference in hydrogen ion concentration. For example, a solution with a pH of 3 has 10 times more hydrogen ions than a solution with a pH of 4. 3. The chemical properties of water. Water, H2O, plays a crucial role in chemical reactions. It is a weak electrolyte and can ionize slightly into hydrogen ions, H+, and hydroxide ions, O-, through the following process: H2OH++ O- in pure water. The concentrations of both hydrogen ions and hydroxide ions are equal. At 10-7 m, this gives water a neutral pH of 7. However, adding an acid or base to water changes its pH. When an acid is added, the concentration of H+ ions increases, lowering the pH below 7. When a base is added, the concentration of O- ions increases, raising the pH above 7. 4. The reaction of acids and bases. Neutralization. When acids and bases react with each other, they produce water and a salt in a process known as neutralization. The basic mechanism of this reaction is as follows: H++ O-H2O. For example, when hydrochloric acid, HCl, reacts with sodium hydroxide, NaO, the following neutralization reaction occurs: HCl plus NaO NaCl plus H2O. In this reaction, the H+ ions from hydrochloric acid combine with the O- ions from sodium hydroxide to form water, and the remaining Na+ and Cl- ions form sodium chloride, NaCl, or table salt. As a result, the pH of the solution moves closer to neutral. 5. The importance of pH and its applications in everyday life. pH plays a vital role in various aspects of our daily lives. Controlling pH is essential in numerous industries, including agriculture, medicine, and environmental management. 1. Biological role. The pH of our body is crucial for maintaining life. For example, the pH of blood is tightly regulated between 7.35 and 7.45, and deviations from this range can prevent enzymes from functioning properly, leading to potentially dangerous conditions. Our body uses buffer systems to maintain this pH balance. For instance, when carbon dioxide dissolves in water to form carbonic acid, H2CO3, it plays a key role in regulating the body's pH. 2. pH in agriculture. The pH of soil significantly affects plant growth. Plants thrive in specific pH ranges, and if the soil becomes too acidic or too basic, it can inhibit their ability to absorb nutrients. Therefore, farmers monitor soil pH regularly and adjust it by adding lime or sulfur to ensure optimal growing conditions. 3. pH in the environment. The pH of rivers and lakes affects aquatic ecosystems. Acid rain can lower the pH of water bodies, which can be harmful or even fatal to aquatic life. Environmental scientists monitor these changes to protect ecosystems from acidification and other pH-related threats. 4. pH in industry. Controlling pH is critical in industries such as chemical manufacturing, pharmaceuticals, and food production. For example, pharmaceutical companies ensure that chemical reactions occur in optimal pH conditions during drug production. In food production, acidity regulators are often used to influence flavor and preservation. 6. Methods of measuring pH. There are several methods for measuring pH. One of the most common is using pH paper or litmus paper. When dipped into a solution, the paper changes color, indicating the pH of the substance. Another method is using a pH meter, which measures pH more accurately by utilizing electrochemical principles. Acids, bases, and pH are key to understanding the properties and reactions of the substances we encounter every day. These simple concepts unlock the complex chemistry occurring in water and in the world around us. The chemical reactions inside even a single drop of water make our world richer and more fascinating. So next time you drink a glass of water, take a moment to consider the chemical processes happening inside. Even in a simple glass of water, there's an amazing world of science at play.